Hi, my name is Paul Wallace. I'm staff at the Nanotech user facility here in this University of Washington campus in Seattle. And today I'd like to walk you through the operation of our micro pattern generator system for doing photolithography and direct write experiments on materials. So this is a Heidelberg Micro PPG laser exposure system, and how it works is we use a laser to focus to a spot onto the sample to do our photolithography. We have a 375 nanometer laser, which is an upgrade from the traditional 405 laser, so we can work direct write with SU8 and also work with our standard photoresists. We have a stage, an XY stage that's controlled pneumatic with interferometry for position measurement that moves back and forth as the fast axis, while the piezo scans 8 microns wide for the fast axis, and then it steps through to expose the energy. We have several motors and several piezos moving in concert to complete our exposure. What we're doing is we're taking our laser and we're moving it in an 8 micron sweep, 8 pixels for a total of 8 microns in this way, and to expose on the sample, we move the sample underneath as we write our 8 micron swath. We then move the stage in Y on the slow axis and go the other way while scanning, moving through every single pixel on the wafer. In addition, there's a piezo in the Z axis, and the way this is working is the lens has an aperture with a known gap between the lens and the substrate. We're blowing air down this aperture and monitoring the pressure. Because the flow rate is fixed with the air coming by the aperture, if the focus stage moves too close, the pressure rises and the piezo backs off. If the lens moves too far away, the pressure drops and the piezo moves back in. That's how we compensate for irregularities in the surface with the focus routine. The focus routine does require to be over the flat part of the wafer, so as you approach the edge and go over the edge, the ability to focus is degraded and eventually lost. For this reason, we recommend a 5mm margin around your wafer, or to simply write with the autofocus off to make sure that your pattern is uniform across all the edges. To start the machine, we want to go ahead and launch the Exposure Wizard, which is the interface with the computer. And while it's initializing, we can go ahead and move our files around. We ask that you transfer your files on the network share and then move them to the local hard drive prior to a write, so you're not dependent on the network connectivity. So here on the network share, I can go ahead and select a given file and then transfer it over to the Shortcuts to Design file for my actual write. We go ahead and select Next. We load our design. It's over in the test design file. I'm going to look at my acceptance standard. I know for this sample, the total write area is 1mm, and that corresponds with a scale factor of 100,000. I go ahead and press OK. It transfers the data from the PC here into the Linux machine inside the Micro PPG, where it's translated and prepared for the write. So we can see that the write area is 1mm by 1mm, and the offset in this case is 0.5 millimeter. I'll explain why that occurs. Now, when designing a write mask, one of the first things you do is you select where the origin 0, 0 is, and by tradition, we generally put that in the lower left-hand corner and design our feature like this. What happens when we move to the Micro PPG is it expects the origin not to be at the edge, but to be at the center. So it will have an offset that is the radius of your circle. With the test pattern we saw, the feature was 1mm square, but the origin was over here, so we had a 0.5 millimeter offset. For a small feature, that's fine, but for a large feature like an entire wafer, you end up only getting a small portion of your design. So when starting off your mask, go ahead and make sure you set your origin at the middle, not at the more traditional lower corner. The radius of a 100 millimeter wafer is 50 millimeters. It's very common to set the radius for 100 millimeters, which is an 8-inch wafer, and not realize the mistake until after you're done printing. So go ahead and make sure you're clear on the radius versus the diameter. We can go ahead and move next. Our next operation is to select the exposure energy. Here 18 milliwatts, and the exposure percent 63, and make sure that we're writing at full speed. The next important step is to load the substrate, and what this does is it raises the optics, moves the stage to the load position, and gives me a dialog. The dialog asks me to open the cover, place the wafer on the chuck, activate the vacuum, and go ahead and acknowledge OK after the cover is closed. If you open the cover at any time outside the instructed dialog boxes, it will give you a fault and the machine will go into emergency stop. So when instructed, go ahead and lift the cover and go ahead and load the dummy wafer. The wafer is put right onto the chuck, and against the alignment pins we set for the wafer. To hold the wafer down for the exposure, we have a vacuum chuck, and we want to make sure that it's held together well. If the position is perpendicular, the vacuum is turned off. To the vacuum on, we rotate it parallel. Likewise, if you're doing a small wafer, you can turn both dialogues off to just have the center vacuum used. We can go ahead and turn on the next portion of the vacuum for a 4-inch wafer. If we're doing a full chrome-on glass mask, we can go ahead and open up all the holes to securely hold the substrate. Today we'll just work with the 4-inch wafer and make sure that it's still bound strongly. After we know the wafer is loaded, we can go ahead and close the cover and press OK on the menu. So we move on to the exposed design. I like to auto unload after exposure. For samples that are not flat or we go over the edge, we can expose with the autofocus off. And we can also use unidirectional mode, which is most useful for grayscale exposures. So to get started, we click the expose button. We see that the machine prepares itself, and it gives us the percent completion and the total time for the exposure. We ask that whenever you prepare a new design, you go ahead and load the dummy wafer and get an estimate of the time so that you can book the instrument appropriately. In this case, my exposure is on the order of 20 seconds, which is relatively quick. For whole wafer or whole mask, exposures are generally on the order of 4 to 6 hours. For SU8 at a quarter speed, it can be substantially longer, so we ask that you check your right time before booking the equipment. Now that the exposure is finished, we go ahead and unload, and that's a successful test write. So when our micro PG is ordered, we have several options. We've chosen to select the 375 nanometer laser over the 405 so we can work directly with UV polymers, including SU8. In addition, we've chosen the 3 micron write head as it writes at the relatively quick 30 square millimeters a minute. The 0.8 micron write head is an option, however the write speed decreases to 3 square millimeters a minute. A chrome-on glass mask takes between 4 and 6 hours at full speed on my machine. On the higher resolution tool, that would take in excess of a day. I should note that the write time is directly proportional to the write area. This machine scans every pixel and either prints it bright or dark. So you go ahead and estimate your area, how wide by how tall, in square millimeters, divide by 30 square millimeters at full speed, and that will give you write time in minutes. Now that we know the time to complete this particular write, we can go ahead and prepare either a chrome-on glass mask from the cabinet, or we can spin photoresist on a wafer or other substrate we wish to write on. So in working with materials, there's a lot of different photoresists you can use and a lot of different surfaces and substrate. I'll cover some of the basics. For most systems, we use a chrome-on glass mask. This is purchased from a company, and it comes on glass with a chrome layer, an anti-reflection layer, and the photoresist already spun on top. This is done in a Class 1 clean room at a commercial facility, and these are ready to go. For our chrome on glass mask, we know we can write at full speed, which works out to 30 square millimeters a minute at 63% power. While chrome on glass masks are interesting, one of the advantages of this tool is the ability to do a direct write either on a 4-inch wafer or an arbitrary substrate. When working with small materials, I request that you have an area of at least 1 inch wide so the focus utility can work. And then we go ahead and load it normally. This is coated with a photoresist, in this case AZ1512, one of my favorite resists, which is 1 micron thick. We can also use a thinner resist, Shipley 1805, which is a 0.5 micron thick. In general, the Shipley 1805 starts at 70% of single speed. The AZ1512 starts at 70% of half speed. However, when we're working with a new material, the glass significantly increases the exposure time. It's necessary to do a dose test to find out the exact energy you should use for a given substrate. The way the dose test works, under Tools, we go ahead and launch the Expose Energy Series routine. We're going to use full power. We're going to do course steps starting at 10% energy and moving all the way up to 100% energy. Then go ahead and load our sample. It's going to write at the center of the stage, and we go ahead and let it run. In general, I'll do a full speed, a half speed, and a quarter speed next to each other, and just move the substrate over by between 5 millimeters and 10 millimeters so that they don't overwrite. So if we move the wafer over, we can do several dose tests on the same material. Here we are exposing the first energy field at 10% power. The stage goes ahead and stops, moves up to 20% power, and launches again, all the way up to 100% power. So when the exposure completes, we can go ahead and develop in the appropriate solvent and develop our solution, wash it off, and inspect our results here on the optical microscope. So with the 10x objective, looking at the exposure series, this example happens to be a positive photoresist where if no light is present, the film remains intact. Upon exposure, the film softens and is developed away in developer step, which is the area here. So what we're going to look for in our exposure series is finding the correct exposure where it's not too little, leaving some photoresist, and not too much, which is obscuring the information. So on this particular sample, you can see that the features still have some residual photoresist in the pattern here. You can actually see that the are 8 micron sweeps as the scanner moves across the sample. So this sample is not enough exposure. We can go ahead and move down the list and go ahead and increase the exposure. And if we look at a different sort of target, we can start to take a look at some of the other features here. In particular, I'm looking for these to make sure that there's a gap in between, and looking at these test features here. This little one happens to be 1 micron, well below the resolution of the instrument, but it's instructive in that you can still see the gap. As we move up in intensity, what we'll start to see is that beautiful gap starts to become narrower and narrower. You can see here that some of them are present, some of them are not. And finally, when we overexpose, we can see that these gaps simply disappear. And from this result, I happen to know that the best and most appropriate exposure is 70%. So we go ahead and count 100% of half speed, 90% of half speed, 80%, where we can see that we're just on the edge. And finally, if we roll back to 70% of half speed, we can see that our gaps are nice and uniform, and this is indeed the ideal condition. If we move down to 60%, we can see that this is also a good value, something we certainly can use, but we start running the risk of being underexposed, where there's residual material left within the feature. In terms of application, we work with a number of materials and substrates here in the lab. We produce chrome-on glass masks, which then go through traditional photolithography to expose the design on a wafer at the cassette level, 20 or 30 wafers at a time, and go ahead and build MEMS, micromechanical electrical systems, devices, parts, assemblies, and other fantastic and amazing things. However, the purchase of the 375 nanometer light laser on this system allows us to do something special, which is direct write of the negative epoxy SUA. So we can load our design like normal. We spin our resist, and as opposed to doing photolithography with a mask, we can just simply load this into the machine and do our lithography with the laser. The advantages are you can write any arbitrary pattern. You don't have to wait for the mask to be generated, and the sidewalls are straighter and higher resolution than if you do traditional photolithography. So this is a typical device. We have an input, we have a thing, and we have an output. The details, of course, are owned by the user. In the middle, we have some very small features which are interesting for the device to function. If I put these on the microscope, you can see, get an idea of what these features do. We have the channel. We can flow material from the input to the output. Is with our direct write, we're making masters. What we have is a positive channel extended above the substrate with holes that cut into the channel. We can go ahead and cast this into a silicon polymer, PDMS, and when we bond that to glass, we have the opposite. We have a channel, a void, now with pillars sticking down for the sample to interact with. One of the advantages of our microscope here is we have a camera attached to it. We can capture a picture. We can select the magnification. Here's the 5x objective. We can go ahead and measure a line. That tells me that the edge to edge of this particular sample is 150 microns, and the center to center is 250 microns. Knowing this allows us to tune our process and optimize the spacing for the chemistry that's desired. I have a number of utilities that are useful for checking and viewing your file prior to write. We suggest that you do this in advance and get an estimate of the total write time before booking the tool. One of the primary software packages I use on the Surface PC is LinkCAD, and this is a converter with a viewer built in. What I'm able to do is open a file format, in this case DXF, saved from AutoCAD. I have a number of options depending on exactly what I wish to accomplish. In general, I'll start with 1 micron for my size scale, but we will select this in the scale factor when we're on the right machine. The precision here is neutral at 1,000 segments. So as we convert a circle into a polygon, we're going to use 1,000 segments. In the output format, I'm also in 1 micron with a scaling of 1 factor. Same arc resolution. Round wires are going to be treated as square-ended, although I suggest you avoid that. We're going to explode text into polygon. I'll go ahead and take that off for now to show you some of the challenges. And we can choose the version of DXF. Depending on what you wish to accomplish with your sample, sometimes flattening file structure improves your result, and generally I recommend using it. But it can slow down the process if you have millions and millions of circles. So we can export polygon as region, or we can close 0 with polygon using solid. These options will depend on exactly what you wish to accomplish with your sample, and this is kind of the default. Over in the next tab, I'm asked to open a file. As we switch over to the view, we can see that this is the North Seattle Community College logo. However, it's shown as a line drawing where these are individual line segments and they happen to be closed. They're not filled in at this moment and they have 0 width, so they're just line segments. One of the things we can do is we can go ahead and fill our object and see that that's the actual feature that's going to be written, and there are some flaws. When we move over to the O, we see that we've defined the outside of the O and the inside of the O. Because these are both closed values, what you get is 1 large O. which is undesirable. As we scroll out, we can see this problem occurs quite often within the text, and we need to do special treatment for this. One clever way is to go ahead and define two separate layers. For example, I have this over here in the corner, and what I've done is I've separated out some, not all, but some of the inside areas I wish to be blank. While this looks perfectly normal in the drafting software and looks fine everywhere else, by using the viewer we can see the conflict, and what I choose to do is a layer operation where I take the A layer, the pink layer, and subtract off the blue layer, the cut layer, A minus B. And for consistency, I'll call this the final layer. When I press OK, I press Start, the subtraction occurs. And if I quickly change the color to something more visible, we can see that indeed the O in north is now correct, where the R isn't, because we haven't done the subtraction yet. Now that we've viewed this logo, when we write this on the machine, we'll see indeed it produces correctly. There's several tricks to doing this, and the trick that the machine has chosen for me is the O is still a complete and functioning polygon, but there's a slight cut. So the machine, or the pattern, is now defined as a segment that travels all the way around, cuts through here, travels all the way around, cuts back infinitesimally small, and rejoins to make the full shape. This is one method of segmenting a figure. And you can see that this is truly infinitesimal. When you're initiating a new project, I always recommend you contacting Ntuf staff. We can meet quickly to discuss your design, make sure that the resolution, the right time, the throughput, and the overall result is consistent with your goals. I often draw a circle centered at the origin as a starting point. I can then add my features either via array or a microfluidic device. We can say 3 inputs generating into a channel with some magic sensor going to an output. So this allows me to center and make sure my device is going to write correctly. So one comment I like to make when you're drawing your designs is this machine works in segments. What it's able to do is closed polygons, starting with a triangle of 3 segments, or a square, a rectangle with 4 segments, or a more featured device. You draw them as polygons, and the machine knows to interpret that this is filled. It won't show it on your screen, but that's how the machine interprets these shapes. You want the line width to be 0, no line width, and you want to keep these in the same layer or as few layers as possible. If you're drawing a line, that's not a closed polygon, so when we go ahead and try to write this, this is open to interpretation, which is generally a poor thing in mass design. So always start with closed polygons. One of the challenges that can occur is if you want to do a feature within a feature, say the R, you can go ahead and define your outside text as a polygon. You can define your inside text as the R, and hey, that looks like an R. When you go ahead and write, the machine doesn't know anything about these 2 samples because they're in the same layer, so it will go ahead and write the entire structure, which is frustrating for your first write. So if you're going to do an R, one way to do this is to do your R as one layer being the R, a second layer being the inside you wish to subtract, and then when you do a subtraction, you end up generating just the feature you want, which is the letter R presented correctly. And this is one of the challenges in design, is to make sure that your features turn out as you like. And the final comment I'd like to make is text is extremely useful. It aids the readability. It adds legends. It tells you where things are, and all sorts of excited things. So text is really important. However, when we're drafting text as an abstract character, and you're telling the drafting program, at this location, put this text. You can always edit the text or change the font or do other things. So when you go ahead and print that, most printers get it right and the text appears correctly, but when you go ahead and try to print, there's no telling what will happen to the text. So if you're working with text, be careful to either break this into line segments. So we have one segment down here within your software package of choice, or check with staff before you get too involved with the text. There's numerous activities or utilities to create outlines. In AutoCAD it's called Explode, and what that does is converts your text to a polygon. Once it's a polygon, we can go ahead and operate it normally as a polygon without having the interpreted layer of text tossed in somewhere down the line. The maximum write area is 101.4 millimeters for your diameter, so we can do a negative mask that's slightly larger. If you go outside that, the data will not be processed or the information will be lost. The resolution is 3 microns, so we're talking about filled polygons that are 3 microns wide, spaced by 3 microns, and the edge roughness is generally submicron, consistent with a chrome mask shop. So it really is able to do high resolution. Occasionally I get requests for toroids with a total dimension of 3 microns with an inside of 1. And at this time with this machine, that's not a feature I can generate. So please stick with 3 micron as the absolute minimum. 5 is better, 10 is better than that. If you're working with a thick material like SU8, try to stick with an aspect ratio between 5 and 10. So if you're doing 50 microns tall, try to limit yourself to 5 to 10 microns wide. As you go taller, the aspect ratio will reduce the minimum resolution of our tool. So for the full-size wafer, 100 millimeters by 100 millimeters square, we're looking at 10,000 millimeters square at 30 square millimeters a minute. That's over 300 minutes, or just over 5 hours for an entire mask write of this size.